Okay, so let's generalize some of the discussion from the previous example. So we were thinking about, well, what does the solution set to this homogeneous vector equation tell us about the three vectors in that equation? And the fact that this vector equation had a non-trivial solution told us that this vector 6 minus 10 minus 6 could be written as a linear combination of the other two. So let's generalize this discussion a little bit. And so if we have a set of vectors v1, v2, up to vp that are all in Rn, we say that this set of vectors are linearly independent if the corresponding vector equation x1 times v1 plus x2 times v2 all the way up to xp times vp equals the zero vector, if this has only the trivial solution. So we say the set of vectors is linear independent if the corresponding homogeneous vector equation has only the trivial solution. Otherwise, if this set of vectors v1 up to vp is said to be linearly dependent if there exists weights c1, c2 up to cp, which are not all zero, such that when we combine these vectors back together using those weights, we wind up with the zero vector. And from the previous example, we saw that this set of three vectors, the corresponding matrix equation, did have a non-trivial solution. So that would mean we would call this set of vectors would be a linearly dependent set of vectors. And that means I'm able to write one of them as a linear combination of the others. And if a set of vectors, on the other hand, is linearly independent, then that means it's impossible to write any one of these vectors as a linear combination of the others. Okay, let's consider the following example. We want to determine whether the set of vectors S, which consists of two vectors, the first vector is the vector 1, 2, and the second vector is the vector 3, 4, are these two vectors linearly independent? So recall that by definition, this means we would want to consider the homogeneous vector equation x1 times the vector 1, 2 plus x2 times the vector 3, 4 equals the zero vector 0, 0. And to solve that equation, we could take a look at the augmented matrix, which would be the matrix that we have over here, the top row being 1, 3, 0. The second row, 2, 4, 0. So we could take this augmented matrix, do row operations on it. So for example, multiply the top row by -2, add it to the second row to do a replacement, and express this in reduced row echelon form, which I've done over here. And so from this reduced row echelon form, we can see there's only one unique solution, which is the trivial solution. So the only solution here is we need to set that x1 is equal to 0 and x2 is equal to 0. So therefore, since the trivial solution is the only solution, therefore, by definition, set S, which contains these two vectors, 1, 2, and 3, 4, is linearly independent because we only have the trivial solution. And we could restate this in terms of matrices by looking at the corresponding matrix equation, AX equals 0. So from looking at the equivalent matrix side of things, we can see that the columns of a matrix A are going to be linearly independent if and only if the corresponding homogeneous matrix equation AX equals 0 has only the trivial solution.